You could certainly break these down into a lot more steps than 3. You could say, for example, step 1, make a list of rates of change. Step 2, identify the variables. But in the end, step 1 really boils down to, this is the main goal before you can get started with the calculus. Use all of your mathematical skills that you have to determine an equation relating the variables whose rates of change you care about. And once you have that equation, you can go into step 2. And in step 2, you can differentiate both sides of the equation with respect to time. And once you've done that, then it's a matter of going back to your math skills. What I'm kind of getting at is calculus is step 2. Coming up with the equation to apply the calculus to and using the equation that comes out of the calculus to answer the question. Steps 1 and 3 are all about pulling together all of your mathematical strengths to get the job done. I know that a couple of you had asked about question number 3, so I want to go over question 3. And again, this morning we went through question 2 on this handout, so I'm not going to go over that again. The length of a rectangle is changing at a particular rate, so what do we have? We have a rectangle, okay? Pretty basic geometric figure. There's a length to it and a width to it. And traditionally what we do is we assign the longest side the designation of L and the shortest side the designation of W, but that doesn't really matter. Let's go through this. Let's sift through this, all these words, and pull out rates of change. It says the length of a rectangle is changing at 2 centimeters per second. Now, that's interesting. It doesn't say whether it's increasing or decreasing. And I know this probably isn't something that we should always, I think it's something that we have to be careful of concluding. If it doesn't say, I think it's reasonable to say that the length is increasing. Okay. Now this is interesting. The width is changing in such a way so that the area remains constant at 20 centimeters squared. So the width is changing. Okay, now I don't know that I want to include dw dt in my list. We'll see. What are we asked to find? What is the rate of change of the perimeter? So I definitely need dp dt in my list of rates because I'm trying to find that. And I need dl dt in my list because I know that. So I really like this question because I'm going to show you a couple of different ways that we could work around this whole width thing. One of them is to take this hardline approach. Since we don't know dw dt, and we can't use dw dt, it would be an additional unknown, we can't use w. We can't use w in whatever it is we're going to differentiate. So now let's go to what we're trying to find the rate of change of, perimeter. We need a formula relating the perimeter and the length of the rectangle, and only those two variables. We don't want anything else in there. Well, the perimeter of a rectangle, and you can look this up on your geometry formula sheet if you like, the perimeter of a rectangle can be found by taking 2 times the length plus 2 times the w, 2 times the width. Or, I mean, you could just look at the rectangle and go, well, excuse me, length plus width plus width. So the problem here, everybody, is we have a w in this equation, but we don't have a dw dt in our list. Just like this morning, where we had, I think it was h we wanted to get rid of. We want to get rid of w. We need to eliminate, and this is going to be a recurring theme through a couple of other problems today. We need to eliminate w because dw dt is neither what we're trying to find nor what we know. Okay? So how do we do that? The key to that is you're told that the area is constant at 20, which means that no matter what the length is and no matter what the width is, 20 is the length times the width. And, you know, if you compare what we're doing in general here to get rid of W to all the work we had to do to get rid of H this morning, it was a lot of work, wasn't it? We had to set up a Pythagorean triangle, and we ended up with a radical. Here, the width is 20 divided by the length. So I'm going to put that in for W in my perimeter equation, and I'm going to get perimeter equals 2L plus 2W, which is 20 over L. And really, that's step one, right? We've got the equation relating perimeter and length. I would recommend, I'm going to go back and show you the work we did with number 2, okay? Which I already did this morning, and I sent out a video link for Buck Mountain students to look at. When we got to, it was an awful lot of work. Where was it? When we got to here, we were basically done step 1, but I said, let's multiply that out. And it isn't that we're just multiplying it out to make it simpler. We're multiplying it out so that differentiating it becomes simpler. And for that reason, with this question, I would be inclined to write the perimeter as 2L plus 40 L to the negative 1, because I think it's easier to differentiate L to the negative 1 than it is to differentiate a number divided by L. So this is step 1. Now there's another way to do this, and we have lots of time over today and tomorrow. We might even do more related rates next week. I don't know. But this is very valuable. There's another way to do this, and I will show you the other way in a bit. And some of you will really like the other method. Others won't. So now I'm ready to differentiate. I can write dp dt equals 2 dl dt. Don't forget you're implicitly differentiating everything with respect to time. Minus, I have to multiply that negative 1 by the 40, so I get negative 40 L to the negative 2 dl dt. And this is essentially step 2. So what does step 3 say that we do? Well, it says that we put in everything that we need to put in to find what we're trying to find. For example, dl dt was 2. So every place I see a dl dt, I'm going to put 2. And by the way, I'm trying to find, Makai, you're one of the people who had asked about this. We're trying to find dp dt, right? Okay. So I need to put in, there's my 2. Now I need to put in dl dt, which is 2. I need to put in negative 40, and this L to the negative 2, I'm going to go back to the meaning of a negative exponent. It's over L squared, right? So 40 minus 40 L to the negative 2 is the same as minus 40 over L squared, which is what I've done there, times dl dt, which is 2, and now it becomes a matter of just, yeah.
Is it 2 the value for dl dt, not L? Because you put 2 in for L. Like x to the negative 40.
Oh, thank you very much. Yes, it is. I need to put in L, not dl dt. Good catch, Ben. So somewhere up here, it's going to have that when statement. When the area is something. When the length is something. I don't know. We're going to have to look. When the length is 5. So we don't... I think we did a problem this morning where it said when the area was something, we had to work on finding L. We don't have to do anything here. It just says when the length is 5. So you're right, Ben. This is not over 2 squared. It's over 5 squared. L is 5, and dl dt is 2. So we can work out what this is. Again, remember, I don't care in this course at this level about exact values, although this wouldn't be difficult. What do we have? 4 minus 80. 80 over 25 is 8 over 5. 4 minus 2.4? Apparently not. What do you get, Mackay? 0.8. Anybody else get 0.8 when you crunch those numbers? So dp dt is 0.8. That's a perimeter, so that would be units of length per second. Correct me if I'm wrong, all of these numbers and units were in centimeters, okay? So this would be centimeters per, make sure it is per second because it doesn't have to be, it is per second. Does that make sense, Mackay? Okay. Now, I do want to show you a different way to do this. And I like this method, and I will tell you right now that this method will be a real time saver for some related rates problems. So I'm going to go back to this statement that P equals 2L plus 2W. And I'm also going to put 20 equals LW. Okay. Now we're trying to find dp dt. So if I differentiate this, and I know there's a problem with this, I'll talk about it again in a second, I get dp dt equals 2 dl dt plus 2 dw dt. And the problem is to find dp dt from this, you don't know dw dt. That's why when I made my list, I made a point of saying the two variables are L and P. We don't want W. Okay? But I'm going to go with it anyway. And over here, I'm going to rearrange this for W and write it as 20 L to the negative 1. And then I can differentiate this and say dw dt equals negative 20 L to the negative 2 dl dt. And I know that many of you are going to see at the end of this, you're going to go, well, it's the same thing. What's the big deal? It won't always be as obvious. I can put this in here. And I get the same thing. And what you can find is that for some related rates problems, you might have 2 or 3 different equations. You might even have a situation where it doesn't work in this case, but you don't know dw dt, but when you differentiate the other equation, you can find dw dt from it. You can actually get the number and then put the number in. There's all kinds of algebraic substitutions that can take place. I go back to what I have told you before. As long as you're following the rules of math, you're not doing anything wrong. If you can tunnel your way to the answer by using proper rules of math and using algebra properly, then you're getting the right answer. Does anybody have any other questions you would like me to go over, other than 2, which we went over this morning, and 3, which we just went over now? Liam.
Would you also be able to put the variable length into the area formula and find width? And then, because it says that the area remains constant, that we're just into the area would be 0.
So my immediate reaction is to say no, but I want to make sure I understand what it is you are asking. So let me summarize what I believe you're asking, and then I'll answer the question if that is what you're asking. What Liam, I think, is asking is, since this formula that you can see at the bottom of the screen contains W, and we don't know dw dt, we want to get rid of the W. So Liam is saying, can we do this? and put 4 there. Is that what you're saying? The answer is definitely no. Because W is a variable, you cannot put it in before you differentiate it. Because think of it this way, if you put W equals 4 there, and you end up with this, then by you saying W is 4, before you differentiate it, you're saying, well, the derivative of 4 is 0, right? You're saying the width isn't changing. You're saying dW dt is 0 because you put in a constant. So this is the bold part at the bottom of the screen here. Can you do that and calculate W equals 4 and put it in some place later after you differentiate it? Absolutely, but you are not allowed to put it in first. And by the way, I don't think we're going to get the same answer. But just to demonstrate this, if we do get the right answer, it's by a total fluke, and I can easily come up with different numbers where it wouldn't work. If you did that, and I'm glad you asked about that, because there's that temptation there to go, oh, I got to get rid of that variable. Let's just dump a number in. This, I'm not going to rewrite it. 2 times 4 is 8. dp dt then would be equal to 2 dl dt plus nothing because the derivative is 0. 2 times 8 is 4. The derivative of a constant is 0. And if you put in dl dt of 2, then you're going to get dp dt equals 2 times 2, which is 4, which is not the correct answer. And you will have to take my word for it that the answer is the correct answer. Yeah.
What I did is I differentiated the area equation and then found the rate of change of the width and then used that differentiated perimeter.
And that's what I was alluding to. Yes, that works. So the other option, and it's kind of what I did on the next page, but I think you're saying you're actually calculating dW dt. So when you differentiate your perimeter equation, for some reason I don't know why I thought we wouldn't be able to do it this way. I think I mixed up which rate of change we knew. You also have, did you put the 20 in for A before you differentiated? And that's good because it is constant. It doesn't change. Now, can I ask you, Liam, did you differentiate it like that with the product rule?
Yes.
Okay. So that would mean 0 equals, the derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. And since Liam knows that dl dt is 2, he's going to, I might as well just erase all of this now. He's going to put 2 in for dl dt. He's going to put 4, which you get from 20 equals lw and L equals 5 in here, which is allowed because you're putting it in after you differentiate, plus the length, which is 5, times dw dt, and his motivation is this, and this is, I love this, it's beautiful. It's a perfect example of doing math properly. There's nothing mathematically wrong with anything that Liam has done here. And he's looking up here at this differential equation. And he's saying, well, dp dt equals 2 dl dt. dl dt is 2 plus 2 times dw dt. So he's going to rearrange this for dw dt. Am I right? Okay. So you subtract the 8 and you get negative 8 over 5. How many of you recognize that negative 8 over 5 as being part of our previous work? You might. Is dw dt. So that goes up here. And you'll get the same answer. Yes, definitely. I thought you meant put the number into your perimeter function. Put it into the perimeter function after you've differentiated. Definitely a solid way to do it. Other questions? Number 9. Okay, so let's take a look at number 9. This is from the textbook. So this is another triangle problem. This is not an equilateral triangle. So this is different than the one this morning. And this is a really good question to kind of summarize related rates. We're given the fact that dA dt for this triangle is equal to 4. And I'm going to put here, Nicole, positive 4 because it says the area is increasing. So, and this is what I mean by being very careful on assuming it's positive. Because if the word said decreasing and you don't see a negative somewhere, you would know it's negative. But since it's increasing, it's positive 4. And the base is increasing at a rate of 1 centimeter per minute. And it says at what rate is the altitude changing? I don't know why. I just prefer the word height when it comes to triangles. I just don't like the word altitude. The when part, and we talked about this yesterday, we've talked about it this morning, I'm going to talk about it again now. The when part is always reserved for after you differentiate. So in the previous question, it was when the length was 5 and the width was 4. But as we learned from the discussion with Liam's strategy, those numbers only go in after you differentiate. So all of that highlighted material, Nicole, goes in after we differentiate. So this is our list of variables written as rates of change. There's a rate of change of the area. There's a rate of change of the base. There's a rate of change of the height. So we need a formula relating those 3 variables. And it's okay to have 3 variables because we have 3 rates of change there. So the formula is A equals 1/2 the base times the height. And that's step 1. We're ready to differentiate at this point in time. And when we differentiate, all 3 of these things are variables, which means that when we differentiate this equation, everybody, there's going to be a dA dt in there. There's going to be a dB dt in there. There's going to be a dH dt in there. And that's okay because of those 3 rates of change, we know 2 and we're trying to find the third. In other words, everybody, I don't need to get rid of anything. You know, if I wasn't told this, if that was an unknown that I just didn't know, I've got a big problem here. I would have to get rid of the B somehow or do a workaround like Liam suggested. There would have to be more information. So let's differentiate, but we have to be careful here because 1/2 BH is a product. So, you know, this is something that we can easily forget about, that when you're differentiating, you have to go back to those product rules and quotient rules. The derivative of A is dA dt. The derivative of 1/2 B multiplied by H will be the derivative of 1/2 B. That's the first part of the product, which would be 1/2 dB dt, times the second part, which is H, plus the first part, which is 1/2 B, times the derivative of the second part, which is dH dt. Is that good, Nicole, to that point? Okay. We can throw in numbers now. Now, we might have to do a bit of running around to find the numbers, but let me highlight what it is we're trying to find. We need to know dH dt, which means we need to put in something for dA dt. Starting left to right, well, we're going to put 4 in for dA dt. Then we have 1/2. We need to put something in for dB dt. Well, you're told that's 1. We need to put something in for the height. Okay. Oh, the height, here it is. The height is 20. Altitude and height are the same. Plus 1/2, we need to put something in for the base. And this is where you run into it's not a brick wall, but you run into a speed bump that slows you down a little bit. Because that highlighted part at the top doesn't tell us the base. But we have this equation of A equals 1/2 BH, and you're told the when part is the area is 80, and 80 equals 1/2 the base times the height. The height is 20. So we have this little we just got to pull over just for a minute, collect our thoughts, and calculate B. So when I simplify this, I get 80 equals 1/2 times 20 is 10, so it's 10B. 80 divided by 10 is 8, so I end up with 8 for a base that I put in. So just to make sure, dA dt was 4, dB dt was 1, h was 20, b is 8, and we're trying to find dH dt. So now all that remains is you have to simplify this and then solve for dH dt. 1/2 times 20 is 10. 1/2 times 8 is 4. So then we can take the 4 on the left minus the 10, which is -6, equals 4 dH dt. Divide both sides by 4. So I'm getting -6 over 4, which is -1.5. And can somebody let me know? Just get some units on here. It would be centimeters per minute. Is that the answer we have in the back? It is. Okay, good. Is that good, Nicole? Perfect. All right, we're going to move on. As I said, we're spending at least 2 more days with this, so there's always going to be opportunity to go back and re-look at some problems that we didn't get to. We're going to do, I believe, 3 examples today. This starts with example 7, which is a continuation of the formal lesson from the past couple days. And I think this is on page 8 of your unit handout. After starting off relatively basic, yesterday we climbed in difficulty, and now we're kind of plateauing again. And then we're going to climb again tomorrow. Okay, so grain is being poured into a conical pile at a rate of 200 cubic feet per minute. So you've got a pile of grain. The grain's going up an auger. The auger is dumping the grain down onto the pile, and it's forming a cone. The height of the pile is always 3/5 of the diameter. And you might think that this is some contrived, made-up thing to make this a doable math problem. There's something called granular consistency with particles. And within limits, the granular consistency determines the ratio of the height to the diameter. It will always maintain that height. You keep piling on more grain, and it doesn't, the cone doesn't start like this, and then as you add more grain, it just gets taller. Or it doesn't start like this, and as you add more grain, it maintains the same height, but it gets wider. It maintains a constant ratio for those things. And let's just write out that as a ratio before we begin here. It says the ratio of, well, it says the height is always 3/5 the diameter. So height, I don't know if anybody has ever taught you this along the way, but is in mathematics means equals. That's what the word is. That's what the word is. That's what the word is means. If I say my age is 55, that means my age equals 55. So the height equals 3/5 of the diameter of the base of the pile. The word of isn't in there, but of means multiplication. So I'm going to use D for diameter. This is an important formula. You're going to see why, I hope, in a very short time. What is the rate of change of the height? I know I'm kind of reading this in a mixed up order, but this is what you're asked to find. And it says grain is being poured into the pile at a rate of 200 cubic feet per minute. Well, cubic feet is volume. So if I'm dumping 200 cubic feet of grain onto the pile in a minute, that means dV dt equals 200. And now you're going to have to go to your geometric formula sheet that I see many of you are already looking at. Because the two variables that we care about in this question are the height of the pile and the volume of the pile. Why? Well, because those are the rates of change that have those variables. And when you look up the volume of a cone, the volume of a cone is 1/3 pi r squared h. Thank you. So, what's the problem here? I mean, the specific problem we're bumping into right now. It's that the radius of the conical pile is in the formula, and r is not a variable in our list of rates of change. So, it needs to go. Unless you are going to find a workaround like Liam did with that one question. And I think there's a really good workaround here, okay, that we can talk about after I get rid of it. By the way, Liam, and those of you who followed what Liam did by having two equations that you're differentiating, most people, that's confusing too, in my experience. If I taught all of the problems that could be done that way, I think I would lose more people than I would gain. So we need to get rid of r. How do we get rid of r? Well, the solution lies in this h equals 3/5 d. Because diameter is 2 times the radius. So I can easily change that to say that the height is 3/5 of the diameter, change it to the height is 3/5 of 2 times the radius. Because that's what the diameter is. And I can rearrange this now for r to replace the r in my volume function. Okay. I'm going to have to multiply both sides by 5 to get 5h and divide both sides by the 3 times 2, which is 6. So I'm going to end up with 5/6 times the height. And if you think it's easy in going from this statement to this statement, I would argue that it's not easy. I couldn't sort that out of my head. I need to look at the algebra. I need to write out h equals 3/5 d, and then I need to replace d with 2r. Some of you might be able to reason out that that's what it is, but I think the algebra is a useful tool here. So why are we doing that? To replace the r in this formula with an expression that has h in it instead. So it's r squared in the formula. I put in 5/6 h as r, and I'm squaring it. Why am I replacing r with h? At the risk of being repetitive, because I don't know dr dt, but I know dh dt. Yeah. If I drop the pi, it's because my brain skipped a beat. The pi should be there. No, it definitely should be there. Thank you. As I was looking out among a couple of furrowed brows, I kept looking back and seeing what I did wrong, and I just didn't see the pi. So now we're going to do the same thing that we have done. Man, I think it's in the last 3 or 4 problems that we've worked on together. Simplify that first. Like that's a fatal error here in differentiating from here. Because then you'd use the product rule and it just gets so messy, so easy to make a mistake. What you're going to do is simplify this. Be very careful because this 5/6 h needs to be squared. The 5 needs to be squared. The 6 needs to be squared. The h needs to be squared. So I'm going to do this in 2 steps. This will become 25/36 h squared, and then we're multiplying by h. I squared the 5, I squared the 6, I squared the h. I don't think it's that big of a deal. Many of you, I'm sure, could have gone directly to this. You could have said, well, I know I'm going to get h cubed. I know I'm going to get h cubed. I know there's a pi. And when I take 5/6 squared times 1/3, I get 25 over, well, actually, let's combine that third right now. 36 on the bottom times 3, help me out, is it 108? So you end up with 25 on the top, 108 on the bottom, and then my pi, which I'll try not to forget. I don't think it's that hard for many of you to take that leap. But I also know from marking many of these problems over the years that this is where the mistake is made. Maybe you forget to square the 5/6, or you square it but you forget about the third. It's a little bit greasy. We're ready to go. This, by the way, everybody, is a coefficient. So when we differentiate the right-hand side, we're just going to swing that 3 down and multiply it and drop 1 from the exponent. And multiply by dh dt. So we get dv dt equals, well, when I multiply 3 by the 25 over 108, in that 108 was a 3, right? It was 3 times 36. So the 3's cancel, and you're left with 25 over 36. And I don't care how you handle that. If you want to go on your calculator, 25 divided by 108 times 3 and convert it to a fraction, you can. This is h squared, and this is dh dt. And, you know, what I would say to you is, for all intents and purposes, we're kind of done the question. It's just a matter now of putting in numbers, and I forgot my pi again, putting in numbers where they belong. So what's the when here? The when is when the diameter is 32 feet. Well, we don't have diameter in here. We have height. But I can use this to find the radius. Pardon me. I can use this to find the radius and just say the radius is 16 feet. Right? Half the diameter. I can put the radius here and solve for h. Interestingly enough, just that part where you see the diameter is 32 and you need to find the height, that's actually kind of a little bit of a tricky little question. Be a good grade 9 question, problem solving, but you need to be able to figure it out. I want to say 19.2. So the height works out to 19.2. Again, this is only the second year I've done this where I've said, you know what, I don't care about exact values. I just want you to be able to do the related rates aspect. You know, next year you're going to have to branch out on your own and learn how to do exact values, but here I'm not concerned about that. We can put in, can I get a yes on 200 cubic feet per minute? Was that what dv dt was? 200 for dv dt, 25 pi over 36. 19.2 squared times dH dt. So, ultimately, I don't know how you're going to figure this out on your own, but this is just a number. 200 divided by that number would give the answer. I would probably do it a different way. I would probably, just the way my mind works, take 200. I would multiply by 3 to get rid of the fact that we're dividing by 3. I would divide by 25 pi, and can somebody tell me what would be wrong with what I've just entered? Oh, it's 36? Thank you. So I would multiply by 36, and I need to divide by 25 pi. Can somebody tell me what is wrong with what I've just entered there? Evan? It has to be in brackets, otherwise it's going to divide by 25 and then multiply by pi. For that reason, this is just what I would do. I need to divide both sides by 25. I need to divide both sides by pi. I need to divide both sides by 19.2 squared. If you choose to calculate this as an entire number first and then take 200 divided by that, that's fine. However you get the answer here is up to you. Make sure I've got everything entered correctly now. 36, 25 pi, 19.2, and just one final double check. It was 19.2. Okay, so I am getting 0.25. Anybody else? Okay, so that is a rate of change of the height, and that would be in feet per minute. dH dt equals 0.25 feet per minute. Any questions with any of the work on that problem? I mean, looking at the big picture here, and you've got it in front of you, right? You can see all of your work. There's a lot of moving pieces to this puzzle. Yeah. All right, let's try the next one. Example 8, a spherical snowball is melting at a particular rate. Find the rate of change of the radius. This is where we're really starting to plateau. This is a relatively simple question. It doesn't require much algebraic manipulation. What we have is a snowball, so it's a sphere. I tend to draw a sphere. When I draw a sphere, it looks like a circle, so I do this like there's some kind of shiny surface to it, and you can see some texture. It's a sphere. So when you're looking at your rates of change, dV dt, this is volume. Cubic centimeters is volume. dV dt will be negative 24 because it's melting at that rate. And we would assume it's melting and maintaining its spherical shape. What is dr dt? Oh, well, this really, everybody, it's probably almost as simple as it gets for related rates problems. Because when you go to your formula sheet and you find the formula relating in volume and radius, it's step 1. Correct me if I'm wrong here, but the volume of a sphere from your formula sheet is 4/3 pi r cubed. Am I right? Okay, so the only variables in that equation are the volume and the radius, and that's what we're dealing with. So we don't need to get rid of anything. We can dive right in and differentiate. I can write dV dt equals 4/3 pi times 3 times r squared dr dt. So this part here is the derivative of the r cubed. I suspect many of you would just move that 3 down in front and multiply by the 4/3. What I'm doing here is illustrating the fact that when you have a constant times a function, the derivative will be the constant times the derivative of the function. If you ended up differentiating from the original equation in one fell swoop and writing 4 pi r squared dr dt, that's great. Tomato, tomato, same thing. Now I can throw the stuff in. dv dt is negative 24. I sense we might have some work ahead of us in finding r, but maybe not. I didn't really pay attention. Does it say when the radius? No. It says when the volume is. So this is that work that we have to do where we're going to use this formula along with the volume to get the radius so we can finish the problem. So this is my side of the road work. Volume, is it 240? Thank you. Equals 4/3 pi r cubed. So I multiply 240 by 3. I divide 240 by 4. I get 180 divided by pi. R is the cube root of 180 over pi. And I want to make a point. You've already got your next assignment, and somewhere on the assignment it says, all work must be done as exact values, and you can round your final answer as a decimal. If this were a written response, I don't want this number, 180 over pi, as a cube root, written as a decimal yet. I want to see it in here. And from there, you can feel free to calculate a decimal for your answer. I don't want to see decimals that are irrational numbers. Well, they're not irrational. I don't want to see irrational numbers pawned off as being some kind of decimals that they're not. Right now, we can go ahead and calculate the RDT, though. So, you know, again, we're in the same boat we were in last time. If you choose to calculate this as a number first, then divide it into 24, negative 24, that's fine. I might do it in pieces. I'm going to do it by calculating that number first this time for those people that may want to. I would start by taking 180 divided by pi. Well, I would start by turning my calculator on. Then I would take 180 divided by pi. Then I would personally raise it to the 2/3 because it's raised to the third and then squared. But if you wanted to, you could raise it to the 1/3. Now we have to square that. Now I need to multiply by 4 and I need to multiply by pi. I'm going to double check all of those. 180 over pi is that number to the third, to the 2, times 4, times pi. So I need to take negative 24 divided by that answer. Did anybody else get negative 0.129? Perfect. So about negative 0.13. What are we doing here? What is this? R dr dt would be centimeters per minute. Good. Any questions with any of the work for that problem? My hope is that as every day goes by, as every additional problem goes by, that it's just starting to become more natural. Because I know that related rates can be difficult. We have one more example I'm going to use today. We have a 12-foot ladder that's leaning against a wall. Somebody has not put the ladder up at a proper angle. By the way, I've always been taught, learned this when I was in construction. When you put a ladder down, if you put the feet of the ladder at your toes and you put the ladder at your arm length, that's safe. If you have to reach further, then it's likely to slip. Okay? So what do we have? Well, let's sketch this. You've got a wall, you've got the floor, and you have a ladder. Ladder is leaning up against the wall. I'm assuming something here, and what I'm assuming is that the wall and the floor are perpendicular to each other, and I don't know why I'm missing something here. Is this 1.5 feet per second in your handout? What is it, Farhan? 11.5. Holy smokes. Somebody's going on a wild ride. I think, yeah, you know what? That's why I have that there. Change it to 1.5. I think that it should be 1.5. That's why I've got that one covered up. I mean 11.5. The ladder is not moving away that quickly. If it is, you know, you've tied your dog to the foot of the ladder and the dog has seen a squirrel and it's taking off. 1.5 feet per second. So if the foot of the ladder is moving away from the wall at 1.5 feet per second, then this distance that I'm going to highlight in pink is increasing at 1.5 feet per second. And you can imagine what happens as the foot of the ladder moves away from the wall. The top of the ladder is going to move down the wall. So we're given d pink length dt is 1.5. Well, we don't walk around in math class saying d pink length. Let's call this something, and let's call it x because it's a horizontal distance. So I know dx dt is 1.5. I want to find d green length dt, but, well, geez, let's just call this something. Let's call it y. And we're asked to find dy dt. Now, what can happen in problems like this is you get used to doing those ship problems or those plane problems or car problems, and you do this. Well, you can if you like, but you don't have to. And I'll show you what happens if you do put a variable there. But in the meantime, I'm going to put 12. Now, I told you earlier, and I made a big deal out of it. I put it in bold in our steps. You're not allowed to put the value in for something until after you differentiate. Why am I allowed to use 12 feet right now at this point in time? Evan? Right, the length of the ladder doesn't change. Now, if it's an extension ladder, and I didn't put the braces in properly, and as this is falling, the length of the ladder is shrinking as well, then I'm really going on a wild ride. Then I would definitely have a z and have dz dt. And that's a legitimate question. I mean, it's not that difficult, but I wouldn't ask it here. I've seen university questions that say, and the length of the ladder is collapsing at 2 feet per second. So then you would have to include it. But we don't here because the length of the ladder is a constant. This is, I think, one of the tamest related rates questions because the equation is just the Pythagorean theorem. Quite frankly, I don't even want to waste my time squaring 12. I know it's 144, but I'm about to differentiate it, and 12 squared is a constant, so it doesn't matter. This is step 1. Step 2 is 2x dx dt plus 2y dy dt equals 0. I mean, I would personally divide both sides of that equation by 2 and get x dx dt plus y dy dt equals 0. I don't know if you've noticed this, but strangely enough, in every area in high school math, I tend to encourage rearranging an equation and then putting numbers in, but not here. Let's put everything in all the time. dx dt, we know dx dt, it's 1.5. So I can put 1.5 in for dx dt. What am I going to put for x? Let's see. What's the when? When the foot of the ladder is 3 feet from the wall. So I'm going to put 3 in for dx dt. Plus y times dy dt. Well, dy dt is what we're after, so I'm just going to leave it as dy dt. How am I going to find y? Because it doesn't say when the top of the ladder is a certain distance from the floor. But I do know that x squared plus y squared equals 144. I can easily calculate y. So my side of the road calculation would be x squared plus y squared equals 12 squared, which means 3 squared plus y squared equals 12 squared. Y squared equals, just help me out here please, 135, which means that's 12 squared minus 3 squared. That means y equals, well, if you were just blindly doing math without thinking of any context, you would say plus or minus root 135. But it's a length. It's root 135, whatever it is. So we can put that number here and pretty much be done with this problem. Take the 3 times the negative times the 1.5, move it to the other side to have root 135 dy dt equals negative 4.5. So dy dt is negative 4.5 over root 135, whatever that is, 0.3 something probably. Negative 0.39 feet per second. And again, we would like to just focus on decimals here in the end. I made that decision last year because, quite frankly, it was just such a lot of time used getting exact values when it's really not important. What did I say, negative 0.39? Feet per second. So, and that certainly makes sense. If the foot of the ladder is moving away from the wall, the top of the ladder will be moving down. Farhan, you had a question.
Would we keep that as negative 0.39 feet per second?
Pardon me?
Would we keep that as a negative, or would we make that positive, depending on the question?
Okay, so it depends on how it's worded. If the question said this, and I have a feeling I know where you're going with this. If the question said, find the rate of change of the top of the ladder's distance above the floor, the answer would be negative 0.39. Does the question say, find the rate at which the top of the ladder is moving down? Then the answer is 0.39. The rate of change of the top of the ladder's height is negative, which means the ladder is moving down at 0.39. I've kind of softened over the years, you know. I mean, if you didn't take that into account, I don't think I would take off marks. I think I would take off marks if you said it's moving down at negative 0.39, because that to me shows a decided lack of understanding of what that negative means. But I am pointing out that next year your TA or whoever's marking your work might get upset. Ben.
I was just making sure when you add the 2x dx dt and 2y, you divide it by.
That's correct. At this point in time, to go from here to here, I'm dividing both sides of this equation by 2. And when you divide both sides of an equation by 2, you're dividing every term by 2. So the 2 cancels, and 0 over 2 is 0. Yeah. I mean, you can feel free to leave those in. What's going to happen is you're going to get an extra factor of 2 here and 2 here, because there will be a 2 here and a 2 here. And it's going to reduce anyway. But yes, that's what happened. Any other final questions with regards to this example? All right, tomorrow we're going to look at, I think 2 more tomorrow. There's only 1 more example in your notes, but for some reason there should be another one. That one that's missing is similar to number 10. If you can figure out number 10, I applaud you. And that I'm giving that to you I'm saying that as a challenge, because I think some of you could probably crack number 10 open, and I would be interested to see what your thought process is without being shown kind of the way it's supposed to be done. Okay. Anyway, you have about 15 minutes left here. Get a couple more of these done, Liam. Yeah. If you need to take a break, take a break. But